Ladies and gentlemen, my name is Monika Kulisz. I am from Lublin University of Technology, and together with my colleagues from my university and also from Research and Development Center Networks SA and this university, we prepare some research about performance analysis of the differential neural network architecture in industrial tomography. So what I will talk about. At the beginning, some words about why we choose this topic, then the aim of the research. After that, I will show you the research object, and I will show you exactly how our differential architecture looks like, which we called multi-stage residual subtraction network. And the final, I will show you some results and conclusions. So why this topic? This year, these authors published in one conference paper where they introduced a model of architecture, which they call diff transformer. And this architecture was defined to improve the performance of languages models. And they use a differential mechanism. So they use subtraction layer, and they use in the context to reduce the attention distributed to irrelevant elements. And they show that using this architecture, they got better distinction between signal and noise. And we thought, because here they use it to language models, what it will be when we use it in tomography. And we try to do it. So as an input data, we use not text, but time of flight measurements. And our previous work, where we introduced this differential neural network, but we use only single subtraction blocks, we already published. It was like 1 month ago. And here you can see this publication. And in this publication, we present that using differential neural network with one single block improve ultrasonic tomography reconstruction. And in this work, we extend this concept into multi-stage residual subtraction network. So we use differential neural network architecture, but we use multiple residual subtraction blocks. And in this case, we use 3 blocks. So here you can see the research object. My colleague Grzegorz Kosowski before explained you some introduction about ultrasound tomography and reactor model, so I won't be describe it again, but maybe I only mention about this tomograph. So we use tomograph where we can measure using 16 transducers and also 32 transducers. And in this case, we use only 16 transducers. And because of that, we got 120 measurements time of flight. And here you can see like experimental environment. But in this presentation, I only show you like simulation results. Our experimental or verification, this idea on experimental data, it's our future work, and we will be doing this like maybe next time. I will show you these results. So to prepare the data for simulation, we have here like 2 things. First is background, so it is tap water. And second, it's like some inclusion artifacts. So in this case, it's plastic tubes. So using final element methods, we use 2 values. First, for background, it was 1006 100, and for inclusion, it was 330. 30. So in our simulation, we use input data, so 120 measurements, and as an output, we got image with 4096 pixels. And this is architecture, what we propose. So as you can see, here we have like 3 blocks. And first we have input data. So it's sequence input data. And this architecture is split into 2 parallel paths. And each of them containing fully collected layer, with 512 hidden units. After fully connected layer, we got due activation function, and one of these paths have scaling layer, which means that the output from this layer, it's multiplied by -1. So we change the sign from plus to minus. And after that, we have like here output and here. And in the next step, we add this output, and this output is input to the next block. And at the end, we have like one more fully connected layer, the same value as the previous one. And at the end, we got a vector with 4096 values. And to compare the data which we got, so reconstruction, we analyzed 2 architectures. First was like this differential, and the second was simple MLP model. So we used, like, when you see this part, like this right part of differential architecture, we got this standard model. So for each fully connected layer, we use 512 hidden units, and also due function. And to check if using this architecture we got the better results, we use the same training parameters. So we use other algorithm, also validation frequency about 100, and validation patient 20, to make sure that we don't overfit these networks. And to compare these results, we use standard quality indicators, so mean square error, peak signal to noise ratio, structural similarity index, and also Pearson correlation coefficient. And here you can see this formula, but it's like, I think that everybody knows this, these indicators. And about results. At this step about training, we saw the first differences. You see on this left hand, we see a training process for differential architecture, and it took less than 5.5 minutes. And for right hand, we see for the standard MLP models, and it took more than 8.5 minutes. So we see that differential architecture model was shorter, has shorter time to train, about 35%. But this is like one thing, yeah, but it's not very important because we don't see results. So here you can see the results, and on the right side you can see reconstruction. And in the first line it's part, and the second it's a differential architecture, so multi-stage residual subtraction network, and the last one it's a standard model. And even when we're looking for our eyes, we see the differences. You see here we see more detail, more sharper, more like exactly objects what we see. Here is like more blurry. And this is like in our using only our eyes, we see that differential architecture, we got the better results. But even when we use quality indicators, we see the same results. So for mean square error, as you can see, for differential architecture, we got about 50% lower errors than for standard. About PSNR or similarity index or Pearson coefficient, we see that for differential architecture, we got higher values, so it means that it's better for us. And now it's time for conclusion. So by cascading these multiple subtraction stages, the proposed differential architecture implements an iterative refinement process that progressively sharpens boundaries, but also restores the structure details and reduces like residual artifacts. And this stage-wise approach allows to focus on like small substantial differences that may be lost when we use only one single differential block. And because of that, we can get higher fidelity in representing object. And when we see the numbers, we see also that errors were like 50% smaller for differential architectures than for standard MLP. And from a practical standpoint, we can say that this approach we can use in ultrasound tomography in industrial context. And this is everything for I prepared today. Thank you very much.